The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Okay, welcome everyone. Our speaker is going to be Hassan Aoude. He is the assistant professor at Ottawa University, and he will be talking about blast behavior of ultra high strength reinforced concrete columns.
Okay, good afternoon everybody. My name is Hassan Aoude. I'm an assistant professor at University of Ottawa, and I'm going to be doing the presentation that my student was supposed to do, Mr. Russell Perel. So I'll ask you to bear with me because this is a bit of a last-minute change. So here's the outline of the presentation. I'm going to start with introducing the material we use, so ultra-high performance concrete, and then CRC, which is a type of ultra-high performance concrete. Then I'm going to look at why we would use this material in blast-resistant design. We'll look at a brief literature review. Then we'll look at the shock tube testing facility at the University of Ottawa, look at the experimental program, and discuss a bit of the results, and if we have time, I'll talk a bit about the analysis. So, as we know, concrete is a very versatile material, but it has some limitation and some shortcoming. So we know plain concrete is weak and brittle in tension and flexion. We also know now we can develop high-strength concretes, but if we do that, sometimes we get a brittle behavior in compression. And also we know reinforced concrete is susceptible to deterioration. So ultra-high performance concrete is a class of innovative material which tackles some of these shortcomings. So when compared to traditional concretes, we can achieve very high compressive strength. We can get good flexural and tensile strength. We can have superior ductility and also excellent durability. So we're meeting some of these shortcomings, and this is why we call it ultra-high performance, because of these qualities. So the material I'm going to talk about specifically today is compact reinforced composite. Basically, it's a ultra-high performance concrete developed by the Cement and Concrete Laboratory of Aalborg, Portland in Denmark in 1986, and currently it's marketed by CRC technology. It has very high compressive strength, so in the UHPC category. It has good flexural strength, and because we add steel fibers at quite high volumes, we can get good toughness and ductility. So here's just some examples of the behavior and compression. This is quite an older study, but it shows that we have good compressive strength and we have some sort of post-peak strength as well, depending on how many fibers we add. Also in direct tension, this is normalized tensile stress versus crack opening. And you'll notice that as we add fibers, we can get some strain hardening behavior in tension as we add more fibers. So it has good tension capacity. Also, it has very good behavior in the fresh state. So this is how it looks like without fibers. When we add fibers, because we're going to, as I'm going to discuss, we're going to add fibers at 2, 4%, 6% by volume, we still get some adequately workable concrete because of the fresh state properties without fibers. Some current applications, so right now used more in some secondary structural applications like staircases, balcony slabs, and you'll notice these elements, they're quite thin, as you notice. Because of these properties of the CRC, we're able to create some of these elements being very thin. However, there's also potential for using this in structural applications. And we're going to look at one today, which is blast. So why use CRC in blast-resistant design? So as we know, it's increasingly important to ensure strategic buildings are blast-resistant. And so if we're talking about a reinforced concrete building, that means ensuring that our columns, ground story columns, are sufficiently ductile and able to prevent progressive collapse. So to ensure this ductility, normally we have to add quite a bit of reinforcement. So we could end up with very highly congested sections. So using these types of materials, we're trying to see, first of all, can we improve performance? And secondly, can we improve constructability? So in terms of a literature view on these materials, so when I say ultra-high performance concrete, I'm also talking about ultra-high performance fiber reinforced concrete. So if we compare to SFRC, there's quite a bit of impact and some blast testing on SFRC. However, if you look at the literature, you'll see much of it is conflicting. So some researchers say you get some good performance. Other researchers say that high strain rates, you're losing some of that performance. There's limited research on ultra-high performance fiber reinforced concrete under impact and blast, and it's a lot more positive. In both cases, there's limited research on full-scale structural elements that are tested in blast. So here's just an example showing this difference between SFRC and ultra-high performance fiber reinforced concrete. So this is a test series by Biding Ganavil and his colleagues in 2002. Just some drop weight impact testing on flexural members made of different materials. So if you look at SFRC, what's showing here on the y-axis is the flexural toughness, and what's shown on the x-axis is the drop height. So larger drop height, we get larger stress rate. And what you see is as you increase the drop height with SFRC, so those are the columns in gray, you'll notice you're losing some of the absorption capacity of the material. So the material is becoming more and more brittle. If we compare with CRC, which is the ultra-high performance concrete that I'm going to talk about, you see it's the opposite trend. So as we're increasing the drop height, we're getting more and more flexural toughness, energy absorption capacity. Come back to this later. Some other examples of potential of this material to use in impact and blast. So these are some projectile tests on traditional concrete and on CRC. And you'll notice that with the traditional concrete, when we put this projectile, you're losing the concrete right away. So this is a very thick reinforced concrete member, whereas with CRC, you're able to absorb this impact. So there's potential for this material in blast. So we're going to talk about blast. So this is just the idealized pressure time history curve that you get when you get a shock wave from a blast. And this shock tube, which is at the University of Ottawa Blast Research Laboratory, can simulate this quite accurately. So the way it works is you have this driver section which is pressurized and a spool section which is pressurized at the same time. Then the air is released from the spool section and it travels in this expansion section over at the end and hits your structural member to impact the blast. So this is what you get from a typical shock wave from the shock tube, and we overlay with the idealized curve, we get good behavior. So let's talk about the experimental program. So here we were testing half-scale reinforced concrete columns under simulated blast loading, and we were looking at the effect of three things: seismic detailing, CRC, so ultra-high performance fiber reinforced concrete, and something I'm not going to discuss too much today, just if we add traditional fibers to our traditional concrete. So we're looking at three things. Here's just the nomenclature, so you know what I'm talking about. So SCC, the first three terms, SCC or CRC, that's the concrete type. SCC will be our traditional concrete, CRC is our ultra-high performance concrete. That's followed by the percentage of fibers, and thirdly, the hoop spacing of our ties. This is what our columns look like before we're casting the concrete. As you'll see, we have two different tie spacings, one for seismically detailed columns, which is at the bottom, and also one which is what we call moderately ductile columns. So these spacings are different to look at two different tie arrangements and configuration. Here's the columns I'm going to discuss. So for us, let's look at the columns which are highlighted in black. These are the control columns. So SCC, we're using SCC concrete in these without fibers, and two different tie spacings. One which is with non-seismic detailing, one with seismic detailing. And this is 50 MPa concrete. So the reason why we use this self-consolidating concrete for our control specimens is because there's another portion to this research where we're looking at traditional fiber reinforced concrete. So because of that, we were using this SCC to be able to better place our fiber reinforced concrete. So that's the reason why we use the SCC. Then we have a CRC test series. So here are 4 columns that I'm going to discuss here. We tested a bit more, but these are the 4 we're going to discuss. So you have 3 of them, which is CRC 2% 75, CRC 4% 75, and CRC 6% 75, which have the non-seismic detailing but different fiber contents. And then the second one, the CRC 2% 38, this one has seismic detailing with 2% fibers. Here's just some properties. The CRC, it was a proprietary material which has a strength of 140 MPa before you add the fibers. Has a water binder ratio of about 0.18, and it comes in prepackaged bags, so you just add the water and the fibers. The fibers, they were 12 millimeter long and 0.4 millimeter in diameter, straight fibers. This is the test setup. So we have our reinforced concrete column. We have a load transfer device to transfer the shock wave as a distributed load along the column height. The supports are partially fixed supports, and we also have an axial load that we're applying to our columns. And when I'm going to talk about mid-span displacements, that's measured by the middle LVDT, which is going to measure the mid-span displacement of our columns. And these are the different blasts that we apply. So I'm going to talk about blast 1, 2, 3, 4, 5, basically just to follow along. It's just different amount of impulse or blast energy that we're impacting on the column. Okay, so you can see this here, the numbers, which are reflected impulse, which is basically the area under the pressure time history curve over the positive phase. And this is what it looks like. So blast 1 was basically a blast to make sure all the equipment was working. So this was to keep the column in the elastic range. Blast 2 was to bring the column just to yield, so the flexural reinforcement, the longitudinal reinforcement to bring that just to yield. And then blast 3, 4, and 5 were there to fail the columns. So let's talk about the results. So we'll start with the effect on mid-span displacements. So I'm going to talk about maximum and residual displacements. So blast 1 and blast 2, so blast 1 was to keep the columns elastic, no real trend emerged from this blast. The second blast, which was to bring the longitudinal reinforcement just to yield, also no real trend emerged. After that, we see the benefit of the different parameters. So I'm going to talk about blast 3 here in this discussion. So here you have a displacement time history. So on the y-axis you have the mid-span displacement, and on the x-axis you have the time. Okay. So what you want to see here is the larger the mid-span displacement, the worse the behavior. So if we look at the first initial column, okay, so if we look at the non-seismically detailed SCC concrete column, you can see it has a very large mid-span displacement, and also you see the residual displacement. So after the load, what's the residual displacement that ends up on the column? So we have this behavior. When we go to seismic detail, we see the maximum displacement is being reduced, and also the residual displacement is much less. So we see the benefit of seismic detailing in traditional concrete columns. If we look now compared to CRC, so here's our same non-seismically detailed reinforced concrete column with 75 millimeter tie spacing, and these are the CRC columns, same detailing in terms of tie and hoop spacing, but different fiber contents. So you can see the maximum displacement here is being significantly dropped here, and also the residual displacements are much better controlled. So you get a lot less residual displacement, so much better performance. If we compare the CRC, again, these have the 75 millimeter spacing, so non-seismic detailing, with the control reinforced concrete column with seismic detailing. You see the CRC not only matches the behavior, it has better behavior. Okay, so this is without seismic detailing. We're able to match the seismically detailed column. We also looked at combination of CRC with seismic detailing. So this first column, 75 millimeter hoop spacing, and then the second column with double the amount of hoops with the same CRC mix. And you can see you get even better performance when you're adding the seismic detailing and the CRC. I'll talk now about the failure mode, the damage tolerance, and the secondary blast fragments. So here's the control columns, non-seismic detailing and seismic detailing. So you can see here at blast 3, the control column failed here without seismic detailing due to buckling of the rebar. If you look at the seismically detailed column, now because the hoop spacing is much less, we're able to prevent rebar buckling, and also you're getting a lot more energy absorption capacity. So it doesn't fail at this blast, there's another blast required to fail this column. So that's the benefit of seismic detailing. If we compare the non-seismically detailed SCC column with the CRC column at blast 3, you can see the difference in terms of damage tolerance. Here's the SCC column which failed at this load, and here's the CRC column. You just have some cracking here, but still almost no damage. If we compare the CRC column without seismic detailing and now with the seismically detailed column at blast 3, you can see also the difference in terms of damage tolerance and the reduction in terms of damage here. We go to blast 4, which is the column that was required to, the blast required to fail the seismically detailed concrete column and the CRC column here. You can see very different behavior between the CRC and the traditional concrete column with seismic detail. These are the failure blasts for the CRC specimens. So what happens is, until you get to the failure blast, you almost see no damage in the CRC columns. But once you get that failure blast, you see the failure is a bit more brittle. So what happens is here, the tension reinforcement ruptured in these blasts in all these CRC specimens, and you get failure at this single crack here at the middle. Okay? So here for the 2% fibers, just to show the effect of fiber content, at 2% fibers, the blast that was required to fail this was blast 4. We went to 4%, it goes to blast 5. And for 2% fibers with seismic, we had to apply blast 4 twice, and then we get the failure. And here's what I was discussing. We get the rupture of the tension reinforcement and the pullout of the fibers here at the critical crack and failure. Here's just to discuss fragmentation. So here's our SCC column compared to our CRC column. You can see with the SCC column, you get a lot of fragmentation as the column fails, whereas with the CRC, you get almost no fragmentation. And this was at blast 3. If you go to blast 4, which is the failure of this particular CRC column at 2%, and you compare it to the SCC with seismic detailing, you see here again you get a lot of fragmentation from the SCC column, whereas for CRC, even at failure, the fragmentation is just in the form of a fine powder. So you're not getting any fragmentation at all. And here's just some videos to show different behaviors of these columns. Okay, so this is the control SCC column at blast 3 with non-seismic detailing. Okay, so here's the column. There you see the fragmentation, and if you look closely at that column, you'll see the buckling of the reinforcement here. So this column failed at this blast. If you look now compared to seismic detailing with a concrete column, now with the reduced tie spacing, at blast 3 again. So now you see better control of the midspan displacement, of the damage, and so on. So you're able to survive this blast. If we look at the CRC column, 4% fibers, non-seismic detailing at the same blast, let's see the behavior. And you'll see almost remains elastic. If we look now at the seismically detailed column, reinforced concrete at blast 4, so the next blast. Let's look what happens here. So now you get lots of fragmentation and you get this failure of this seismically detailed column. Okay. This is the CRC column with seismic detailing, 2% fiber at the first application of the same blast. So you'll see same sort of behavior. You get a lot more damage tolerance and almost no damage. And then if we apply the blast 4 again, now we're getting failure. And the reason is, if you looked at the first part of the video, when you applied the first blast, you saw there was a big opening of the crack right at the mid-span. So that might have caused the pullout of the fibers at that time. And this is just a side note, just to show that we did some research also with SCC with fibers, so traditional SCC with fibers. And you see you also get good performance just by adding fibers to your traditional concrete mix. So you're reducing the displacement in this case. And the same thing, you're able to match a traditional SCC concrete column with fibers, but without seismic detailing, you'll match the performance of a seismically detailed column. However, in terms of prevention of rebar buckling, you're not able to do that with the SCC and fibers in our test series. So the CRC behaved better in that sense. I'll just talk quickly about the analysis. One more minute, okay? So we just did single degree of freedom analysis. So very simple analysis here. So we just looked at this sort of lump analysis analogy. And we used a program called RC Blast, which was developed at the University of Ottawa. And this was able to go through these steps. So I'll skip these because we're running out of time. But basically, we just have to include the material properties, and then it generates moment curvature, and then we're able to get resistance function and get finally do the single degree of freedom analysis. So here's an example of the input of the material properties, the cross section, and then you get all this output. And I could talk about the models, but I guess I'll bore you with that. So just to show you some of the material models, and we can see we get very good comparison between experimental and analytical results for traditional concrete and also for CRC. So it's a suitable method for that. So in conclusion, we saw seismic detailing can improve the blast performance of columns in terms of displacements. Similarly, we saw CRC can reduce displacements, improve damage tolerance, reduce secondary blast fragments, so it improves blast performance as well. And finally, I showed very quickly the single degree of freedom analysis can be used to analyze these types of columns. Thank you very much.
We have time for one very quick question. Any questions? Can you walk up to the microphone?
My question might be simple, but I would like for you actually to explain to me how exactly does the fiber change the behavior of concrete at the higher level of blast? What kind of mechanism actually triggers at that level that transfer all the load carrying capacity or absorption of the energy capacity all the way from the concrete as a new material to the actual fibers?
Okay.
What is the magic?
Yes. So it's not really just under blast. In fact, there's...
You can just talk.
Okay. So as we know, fiber reinforced concrete, we just compare fiber reinforced concrete to traditional concrete. What's the main difference? We're able to get some tensile capacity and some post-cracking resistance. Same thing with this material. So if you're looking at the column, it's tested, the blast wave is basically testing it under flexure. You have some axial load and you're getting some flexural capacity. So if you can improve the tensile capacity, that's number one. The fibers are helping there for sure. So you're getting better performance. Added to this is you're applying axial load. So we've done some tests on axial loaded columns. What you see when you add fibers, you're getting confinement, improved confinement. So that as well improves some behavior because you're able to improve the behavior of the material in compression, and also the fibers are able to improve the material in behavior and tension. However, the high stress rate that we're applying, some research has shown that traditional fiber reinforced concrete, you lose some of these advantages. With this ultra high performance fiber reinforced concrete, you seem to be able to maintain some of that. Yes.
So it's just improving the tensile capacity is good enough to improve the performance to that level.
Tensile capacity, compression behavior, and also damage tolerance. So if you looked at the concrete column, what's happened, you get a lot of fragmentation, you're losing a lot of the cover, everything else, right? So you're improving the behavior in several aspects. So tensile capacity, compression, behavior, also damage tolerance, all of it together, it gives it.
Stiffening action? Is there a stiffening action of it?
Yeah, you can get some improved stiffness as well. That's right. Yes.
Thank you.
Yes.
We are out of time, but I saw some people have questions. Our speaker.
Special reinforcement.
What did you use for reinforcement?
We use longitudinal reinforcement, just regular reinforcement. So grade 400 MPa, so what's used regularly in buildings. Yes.
So if you have other questions, you can ask the speakers.
Same type of hoops for both the seismic and non-seismic?
Yes, same type of hoops. Yes.
Same configuration?
Yes, same configuration.